everybody. Welcome to tonight's webinar. We are so excited to go over 2 ways to explore Newton's second law. As folks kind of get settled into the Zoom room, I'd love to encourage you to navigate down to the chat bubble at the bottom of your Zoom window. It looks just like a little chat bubble from the comic books. If you click that, you'll be able to send us a chat. And I'd love to remind you that if you send a chat in the chat box, please make sure it's set to everyone so that everyone can see what question you've sent. During today's webinar, Fran and Josh are going to be answering questions live, and we ask that you send your chats to everyone so it doesn't look like they're talking to themselves. So please make sure you set it to everyone. To go ahead and practice, please let me know. Let's see. What kind of pet do you have in your home? I'm a crazy cat lady. I've got 2 cats myself, but I'd like to get those numbers up. So go ahead and navigate to the chat bubble and let me know what kind of pets you have. I wonder if, oh, we have a dog. Lovely. A plant. We are a big plant household. That is so valid. 2 cats, 2 dogs, nice and balanced. Very cool. Does anyone have maybe a lizard or a snake? I don't know, something kind of out there. Let's see. Labrador retriever, so sweet. A dog, a doggo, a cat. Ooh, Fran has a radioactive cat. That is what I was looking for. Nice, 2 dogs. All right, and then just as the last few people are popping into the Zoom room, please remember to set your chats to everyone so that we can all see your questions and we all get to benefit from the shared knowledge. To make the most of our time today, we'll just hop into some quick housekeeping items, and then I will pass the stage off to our amazing presenters. The first of my housekeeping items, I want to let you know that you will get a recording of today's webinar. It usually takes us about 3 to 5 business days to edit the Zoom recording and put it onto YouTube, but as soon as it's live, you're going to get an email with a link to it. Inside that follow-up email, I'm also going to get you a link to today's resources folder. And inside that folder is today's presentation, some experiments you can do. I'm going to put a link to that folder in the chat right now so you can follow along on today's presentation. And there's some clickable links in there for you all too. The second housekeeping item I want to cover is just reminding you that we want to answer your questions. So if you have a question during today's webinar, please feel free to put it in the chat bubble or in the chat box. Fran and Josh will be answering questions and we'd love to hear from you. If we happen to not answer your question, please reach out to us. You can reach us at physics@vernier.com. That being said, I will pass you off to Josh and Fran, and thank you again for joining us today.
Thanks, Dylan. Welcome, everyone. We're glad to have you here. I'm talking about Newton's second law. By way of introduction, we'll do some introductions first. We'll talk mostly about Newton's second law, mostly in the context of like what we would call a 3-dimensional lesson, like what it would look like if you wanted to teach Newton's second law through the inquiry cycle. We should have some time at the end to answer some questions if necessary, and Dylan will then wrap up and tell us a little bit about when she'll send her email. We want to know a little bit about you, so I can kind of tailor our discussion here to the folks that have arrived. And so Dylan's going to post up a poll through Zoom if you'll answer those 3 questions. In the meantime, while you're answering those, hi, I'm Josh. I used to be a high school physics teacher. I taught in Northern Virginia. I taught everything from conceptual physics to AP physics. So a few years of engineering in there as well. Here at Vernier, I do trainings like these. I also do a lot of customer service work. So if you call or email or use our little chat window on our website, you might reach me. And then I help with product development, and I get to attend conferences and that sort of thing. I'm joined by my colleague Fran, the director of physics here. She's also has a very similar background. She spent a lot of time high school physics. She knows a ton of stuff. I'm really glad to have her as my backup because chances are she knows the answer to the question. Um, like Dylan mentioned, if you have questions, please feel free to post them in the chat. We'll try to answer them. Fran's going to surface ones that are especially good ones that everybody will want to hear the answer to me, and we'll answer them there, kind of online here. And
Speaking of questions, Josh, we already got one about what school did you teach in Northern Virginia?
oh, I taught in Fairfax County Public Schools. I taught at Herndon High School, and I lived for 10 years in Herndon while I taught there, and I really loved it. Oregon's great, but I have a lot of sentimental attachment to Virginia still. All right, I see the results of our poll here. It looks like we've got a lot of experienced users, a lot of folks. Well, it seems like everybody's already using Vernier products. That's great. I hope you're making the most of them. Webinars like this, a lot of the purpose or reason why we do it is so that because we want you to make the most of it. And we've got a few college instructors as well. That's great. Everything we do here today will translate real well to a college class as well. Let's talk a little bit about. I'm going to use our Graphical Analysis Pro software. You may be familiar with it. You know, we've been using it. We've been developing graphical analysis for the last several years. The Pro version is the paid license version of that. You can buy it as a 1, 2, 3, 5-year license. If you've never used it before and you'd like to try, there is a link here. I'll post it in the chat. And it'll prompt you to you can either download it and install it, or you can just have it run within the Chrome browser. It needs to be the Chrome browser. But if you click on that link, it'll just load it within the Chrome browser itself. That's how I'm going to use it today. You can do it either way. You'll see that link that I posted has a key equals at the end of it. That's actually the license key. It's good until, I believe, October 21st or something like that. Later in the webinar, I'll collect some data and I'll share it kind of online. So if you have graphical analysis open, you'll be able to get a copy of that data as well. All right. So when you think about teaching Newton's second law, there are lots of ways of doing it. A lot of times what you want are your students to have the experience of like discovering that law. You want them to think about a situation that would prompt them to look for, where the principle that's demonstrated here is Newton's second law. And you want them to gather data, analyze that data, and come to this understanding that the acceleration of an object is directly proportional to the net force on it and inversely proportional to its mass. And that's the way I'm going to talk about it today. That kind of like that learning cycle of discovering this. We call it, sometimes it's called the inquiry cycle. There are lots of names for it. But that's what we're going to go through today. So I'll present a phenomenon, talk about ways you might use that phenomenon with your students to kind of prompt the investigation. We'll talk about what the investigation is, and we'll talk about setup tips and stuff like that, how to best use your motion detector and that sort of thing. What the data will look like and the analysis you'll do, and then how they might expand once they know the idea of Newton's second law, where they might apply it elsewhere. The next generation science standards and the Texas standards all address Newton's second law. It's kind of one of these core ideas. It's not surprising that it's in there. The NGSS I've been learning more about recently, and I've been surprised by how little it talks about kinematics, but how much it does talk about things like Newton's laws of motion and the conservation laws. One of the things that sets the NGSS and the new TEKS apart from our older standards is that it directly addresses some of those things about science that chances are you're already teaching, but they do it in a much more explicit way. The idea that there are these cross-cutting concepts, these principles that show up in every science. So things like cause and effect, or energy and transformations and that sort of thing. And it teaches the science and engineering practices, things like analyzing and interpreting data, or constructing explanations, or using mathematical models. So when we design a lesson or plan a lesson around Newton's second law, and we want it to kind of have this complete three-dimensionality to it, the standards, and then the cross-cutting concepts, and then the science and engineering practices, we want to make sure we do things that bring all three of those in. And the way that as I've been learning about these new standards and how we create lessons around them, one of the things that's kind of like stuck with me the most is the idea that we want students to make sense of things. And if you have them engage in the sense-making process, they're naturally going to learn the standards or the content. They're naturally going to engage in these cross-cutting concepts, and they're going to use the science and engineering practices along the way. So I like this idea, this model of using a phenomenon as a way to prompt, a laboratory investigation. Before students do what we're going to do together today, they should know things like, they should know about acceleration. Chances are they've already done a kinematics unit, and they know a little bit about rates of change and that sort of thing. They should know about what kinds of forces, things like gravitational force and tension and friction and that sort of thing. And they should be able to draw free body diagrams. If they know those three things, they're in a good place to be able to understand what we'll talk about today. If they haven't, then you might want to do some introductory activities to help them, get some experience there first. All right. So the idea here around the inquiry cycle is, first we're going to share a phenomenon. I'll share that with you next. Basically, it's a YouTube video that shows a race between a motorcycle and some cars and a fighter jet and that sort of thing. You'd share this with your students. You discuss it, like what kinds of things, what do you observe in this? Why do you think it happens the way it is? And what kind of things would you investigate to help understand or explain that phenomenon? We're going to use a simplified experimental, our experimental setup is going to be kind of a simplified model of what we're seeing in the video. And then we'll have students, I typically would have them, if you have enough time, you could have both, but typically you'll divide your students in two groups. And so one of the groups will measure acceleration versus net force, and the other group will measure acceleration versus mass, total mass. And then you come back together, they share their results, they kind of talk through these things, and you can build Newton's second law from the results of those two investigations. And then, because you start with this phenomenon, you want to end with it as well. And so you loop back to that phenomenon and say, okay, now that we know about this, the relationship between force and acceleration and mass, how does that explain what we've seen here in this video? And then you give them an opportunity to then apply it to new situation. That's kind of like the cycle there, and that's what we'll go through today. So first, this is, I just found this on YouTube. I used a version of this when I was teaching in the classroom. It was a different one. This one has much higher resolution. But essentially, it's a race between a number of vehicles. And you can kind of see, this is the first frame in the video here. This is the super bike. It's a very powerful bullet bike, motorcycle. This is a Formula One race car, a variety of high performance cars. And then you can see there's a fighter jet here. And then on the other runway, there's also like a kind of like a private jet sort of thing. And you can watch this. It shows the race from various perspectives, which is kind of nice. You can kind of get a sense for how they're moving relative to each other. You can kind of see the passenger jet is kind of the slow poke in the background there. And if you were just to ask students which is going to be fastest, they're probably going to tell you, oh, well, the fighter jet for sure. I mean, it's flying, right? But in this case, you can see that the motorcycle actually pulls out front and takes the lead. And students might understand, well, oh yeah, what's happening there, because they know a little bit about acceleration. They can see that the motorcycle has the greatest acceleration. But then that begs the question, wait a minute, why does the motorcycle have the highest rate of acceleration? And so I love this because it's a great thing. You can ask students to do it. It's got this kind of like discrepant event thing going on where you're kind of like, well, why is it like that? If I were to teach this in my class, I would probably show this towards the end of class as preparation. Like, we're going to do this a lab activity next week. Here is a video that's going to kind of prompt what we're doing, and you'd ask the student, you show the students. The question is, how can the superbike kind of outperform these other vehicles? And then you might ask them some, you might ask them some follow-up questions. Like, I want you to create velocity versus time graphs for the superbike, the fighter jet, and the Formula One race car. You might have them do some research on the vehicles, like, how big is it? How heavy is it? How much horsepower does it have? You might ask them to list factors that would affect the vehicle's rate of acceleration. Like, we're just starting from a dead stop here. What factors do you think might affect that? And they might say things like, oh, well, what kind of engine it's got, maybe the tires that it uses, maybe how big it is, or its size, or its shape might be important. The idea is you just want them to get thinking about the phenomenon in terms of explanations. Why might this be happening, right? In terms of quantities that we can measure, and you want to kind of preload any sort of things they might already know about vehicles or cars or acceleration, that sort of thing. So I would do this on like in a pre-lab sort of thing, right at the end of class. Next class we're going to do this lab activity. Here's this video I want you to do, and you might have them do a few of these things as part of their preparation for the lab activity the next time. And then on lab day, they show up, and you show them the experimental apparatus, and you say, okay, what we're going to do is we're going to create an acceleration in these dynamics carts. And we're going to be able to vary some factors. And you can talk them through that process of which factors you're going to vary and how you're going to do that. This particular lab activity, this is this modified Atwood's machine setup. We kind of talk about this if you want like an experimental, or if you want a lab to be able to refer to later. You'll have these slides. But I also, in the folder that Dylan shared with you, I also put a couple of PDFs of the student and instructor versions of this lab, Newton's second law, from our physics explorations and projects book. And this has a lot of the kind of, especially a lot of the details that I share in this presentation today are also that came from the instructor notes of that lab. So it'll be a great resource to you. Okay, so you've got the experimental setup. Students understand they're going to be measuring acceleration, and they're going to be able to test two different things, mass and force. And when you walk them through this, it's kind of easy to say, okay, if I want to change the mass, that's easy. I've got these hexagonal masses that just like I can plunk down on my dynamics cart, and it adds some mass, and I can see how that affects the acceleration. With changing the net force, it's really tempting for students to just say, oh, I've got this hanging mass on the end of the hook here. I'm just going to just add more and more mass to that. And they might, it's not as easy, it's a little trickier than they want to think. And so you might have to walk them through the process of thinking about what is the system. Well, when I add mass to that hanging mass, what am I changing? I'm certainly I'm changing kind of like the net force on it, but I'm changing something else as well. If students are thinking of the system just as the cart, I've got this cart on the track, it's getting pulled. It's easy to say, just to understand why they might do that. That's kind of like my focus of my attention here. And they might think, okay, well, the tension on that string, that's the thing pulling it along, the thing accelerating it, so that's my force. And you've got this hanging mass here, and say, okay, yeah, well, I know, I can weigh that hanging mass. I can figure out how much it's pulling on the string, and there we go. We got our force. But it's not that easy, and that's because the tension of the string isn't the same as just the weight of the hanging mass. We know as instructors that if the two were the same, the hanging mass would just stay motionless, and that the reason why it's accelerating is because the force of gravity is greater than the tension. So if we wanted to just measure it, we just wanted to measure the tension in the string somehow, we could mount a force sensor on top of our cart, And we can do it that way. If you have force sensors, that's not a bad way of doing it, right? You mount the force sensor on there and you have the string hanging off, and then you can just directly measure the force. If you don't want to do that, or you don't have force sensors, you can do some math and use the, like the mass of the weight of the hanging mass and the string. You can calculate the tension force, but that kind of assumes you already know Newton's second law. And we're trying to take a step back here, and we want students to kind of discover Newton's second law by themselves. So rather than that, you might have to do a little bit of explaining or some discussion around the system. The system that's moving here that we're going to pay attention to is the cart and the hanging mass. And the rationale behind that is typically that both of them are moving, they're both accelerating, and they're accelerating at the same rate, so we can treat them kind of like one object. In that case, the tension force connecting one object in our system to another object in the system is like it's internal. It's pulling forward on the cart, but it's also kind of pulling backwards up on the hanging mass, and those two forces basically cancel each other out. Which means that the only external force, the force that's accelerating the system, is just the weight of just the hanging mass, just the weight of the hanging mass. In that case, we can measure that. That's easy. You can put it on a scale and you can measure what the mass is and multiply by 9.8 to get the weight of the thing. And then you can say, okay, well, that's the weight of my hanging mass. That's my net force. And I know that the mass of my system is the total mass of the cart plus the hanging mass. That means if I want to measure acceleration versus net force, I can't just pile on more and more mass onto the hanging mass. That changes the weight, the mass of the whole system. So instead, what you do is you move you move mass from the cart onto the hanging mass. That way, the total mass of the system stays the same, but the net force on the system increases. I've collected some data. I'll share that with you in a minute here. But that's kind of the rationale around that. All right, so you're going to measure, you've got these, you want to measure acceleration versus force, net force, or acceleration versus total mass. And I'm going to talk a little bit about the motion detector. We've had a variety of motion detectors. The latest one is this one. It's the Go Direct Motion Detector. But you might have, in your classroom, you might have these older LabQuest motion detectors that have like a pivoting head and a sensitivity switch. The latest version is green. There's a version that's black called Go Motion that you can use, just plug in. It has a USB cable instead of one of these BTD cables. And then there's an older version that's kind of like a teal color. They all kind of work on the same principle. They emit like a 40 kilohertz sound wave. It goes out and hits your target, and then it listens for the reflection of the echo of that sound wave. And it knows at what time it sent out the sound wave. It listens for when it hears it come back. And from that round trip time, it figures out how far away the object is. And one of the things that's great about motion detectors is they're really versatile. Today, we're going to measure carts, dynamics carts, but you can also use it with people or like a basketball. If you're going to use a ball, like something like this 8-inch Nerf ball is perfect for it, especially since if it lands on a thing, it's not going to break anything. Some things you should know about is it's one-dimensional only, so it's only measuring what's directly in front of it. Well, it's best to imagine like a cone with a vertex of 30 degrees centered on this gold foil transducer here. This is actually a very high sensitivity microphone that's tuned to that 40 kilohertz signal. It's listening for it. Basically, imagine anything inside that cone, it can see. Anything outside that cone, it can't. So it's really just one-dimensional motion and directly in front of it. It measures position. Well, it measures time and then uses that to figure out position. In the software and graphical analysis, it'll then do a numerical derivative to find the velocity and then also the acceleration. We'll look at that today. When you use it with carts and tracks, there is a cart mode in the software. I'll show you how to turn that on. That basically just makes it listen for much smaller reflections, like you might get off of a cart. And then there's when you're using it with carts and tracks, the newest version, well, I should say, relatively new versions of the cart and track system that we sell has actually a reflector plate on it. That's, I'll show you here. That's this little reflector plate that is just kind of magnetically stuck to the end of the cart. The last thing you should know is that if you're too close to the motion detector, it gets kind of confused. It's sending out a pulse, a sound wave, and when it does, it creates that click, that pulse, the whole body of the motion detector kind of resonates with it. And because of that, if the sound wave is returned too soon, it doesn't know, the motion detector doesn't know if that sound, what it's hearing, is coming a reflection from the target or whether it's the case still resonating with it. And so there's like a dead zone, about 20 centimeters or so, directly in front of the motion detector that you don't want to put your object there that you're tracking. In our cart and track systems, it comes with this kind of like long, flat rod. This is designed to mount your motion detector on so that you can attach it to the end of the track and that dead zone isn't taking up a part of your track, you know. I didn't know about these rods, and in my own classroom with my motion detectors, we would just put a couple of physics textbooks at the end of the track and then just sit the motion detector on that and do it that way. Work just as well, but that way you can use the whole length of the track rather than just, you know, a portion of it without having to worry about that dead zone. All right. I'm going to mount this to my track here, and then I'm going to switch to graphical analysis. I'm going to collect some data, and I'll share that with you. If you want to try this out and you want to open up Graphical Analysis Pro someplace, you can use that key, that link that I shared earlier. And yeah, we'll go from there. So I'm gonna move this, put this back on the end of my track. I'm gonna bring this over here real quick so you can kind of see where I'm going, what's gonna happen here. All right. So I've got my dynamics cart. It's got this little reflector on it. I have a string. I'm going to connect it to my cart. And then I've got a hanging mass over here. I actually have like a little step stool here down below to catch my hanging mass. Usually you're doing this in a lab group, and so it's not you've got somebody to catch the hanging mass for you. I have a piece of tape on top of my cart here. That's just so when I'm doing the investigation where I want to move the mass from the cart to the hanging mass, I can just stick those down real easily. If you're doing an investigation where you're just measuring, you're changing the mass of the cart itself, these hexagonal masses fit real well in the carts themselves, and you don't have that same, you don't really need the tape in that case. All right. I'll put this back down here. I'm going to move to the software next. And I want to go to graphicalanalysis.app. I'm going to do the same link, and I'm just going to have it open in the browser. And the first thing I'm going to do is I'm going to connect to my motion detector. Actually, first thing I'm going to do is going to make this a little bit easier for you at home to see what I'm doing. Okay. So I'm going to connect to my motion detector. So I'm going to go here to sensor data collection, and it's going to ask me if I want to connect via USB or wirelessly. I'm going to choose wirelessly because it's kind of over there a bit. And I'm going to look for my motion detector on the list here. Chances are, if you're doing this, you're not going to see a big long list like I do, but I'm in the Vernier offices here where there are lots of Go Direct devices. I've connected to this motion detector in the past on this computer, so it says it's paired. It's not actually paired. It's just, it's saying you've paired with this in the past. So I click on that and I hit pair, and then it's going to set up that link, connect them two together. I know it's connected. I can hear it. You probably can't yet, but it's like doing the little click. Before I move on from this screen, though, I want to show here where it says sensor channels, the default is motion. If I click on this little triangle, it's going to show me other options, other channels on the motion detector. The one that I'm going to choose is cart. That means it's like a higher sensitivity. This is like you know, that slider switch on the older motion detectors. There's one for people and balls, another one for carts. This is kind of like the same sort of thing. This last option is motion with TC, stands for temperature compensation. So if you were to do an experiment outside someplace where it was noticeably cooler or warmer than room temperature, 20 degrees C, it will actually measure the ambient air temperature and adjust its calculation for the distance that it's traveling, you know, because the speed of sound changes with the temperature. That's not a problem here. So I'm going to choose motion cart, and then I'm going to choose done. In the lower right corner here, I've got a live readout of the position. I can see that it's set up as a position versus time graph. I'm going to measure, I want to measure acceleration, and I can do that, get that from a position graph, but I'm going to switch to velocity just because that's where I'm going to end up anyways. I'm going to do a curve fit on the velocity graph to find the acceleration. So I'm going to go here and I'm going to switch. I'm just clicked on the vertical axis label here, and I'm going to choose velocity instead of position. You can see it kind of rescaled things so that I can have positive or negative velocities. And I'm going to collect some data. It's set up, I can see from the graph here, it's set up for 5 seconds data collection. That's more than enough for a simple thing like this. What I'm going to do is I'm just going to pull my cart back. I'm going to hit collect. I'll hold it there for a sec and then let it go, and it's going to accelerate down the track. And then I'll come back to I'll come back to it and I'll analyze it. If you are, oh yeah, I'll share my data here in a sec. But first, we're just going to rearrange things a little bit so that we can have both the graph and our image here. Okay. So I'm going to take, and I'm going to go here. And I want to go. I'm going to go here. And I'm going to hit collect. I'm going to wait a sec, and then I'm going to let it fall. So I need for longer arms. Okay, here we go. I caught it so it didn't make too big a bang here. And you can kind of see I got a little blip. This is accelerating, and then I caught it and slowed back down. I'm going to make this a little easier to see. So I'm going to go, I'm going to stretch this one. And I'm going to zoom in there. I can kind of see, you know, this is what I want. It's a nice clear acceleration here. And if I click and drag on this portion of the graph where it's speeding up, I can then choose apply curve fit, and this allows me to do a linear fit on it. That's what I want. I'm going to hit apply, and right off I get y equals mx, please. It gives me a slope. Now, if you'd like a copy of this data at home so you can try this out, what I'm going to do is I'm going to hit this, I'm going to share this data. And the way that I do that is I'm going to use this little, I don't know, sometimes the developers call this the TIE fighter. I'm going to click on this, start a data sharing session. I'll hit start session. And what you want to do at home in graphical analysis is you want to start a new experiment, and you want to choose data sharing. And when you choose data sharing, it's going to ask for a data sharing code, an ID, and that's this one right here. I'm gonna copy and paste it, and put it into the chat. You can copy and paste that into your data sharing code, or you can just put it's always 6 digits, just 6 characters, one number in the middle of it all, RMV2QN, all lowercase. If you plug that into that data sharing section there, what it's going to do is it's going to go to find a little website, and it's going to use that. It's going to download the data from my data here, from my copy of graphical analysis, into your copy of graphical analysis. You'll notice you just get the data. I've already done a a curve fit here. You don't get that. You only get the data. I'm going to do another run, and we can do you'll get that as well, so long as you're still connected. So I'm going to add some more. I'm going to add some mass to my part to make that so we get a different acceleration this time. I'm going to pull this guy back, and I'm going to do the same thing. I'm just going to hit collect. I'm going to wait for a sec, and then I'm going to let it go. All right. Okay. I got some noise there. That's the idea. Actually, maybe I just got noise. Let me try that again. Oh, hey, there we go. That looks more like it. I think before I bobbled it. Anyway, I'm going to zoom in on this. And you should have gotten a copy of my bad data. You should also have gotten copies of this better data. If I do the same thing, I'll do and select the region here where it's accelerating nicely and use apply curve fit. I can do a linear fit on that. And I added 2 of those hexagonal masses, and I got a noticeably lower acceleration. If I want to see both of those side by side, those 2 curves, I can choose data set 1 and data set 3, selecting it from the vertical axis label here. And I can see here's run 1, there's run 3. This was with no added mass, and this is with those 2 extra added mass. And I can see the slope is significantly different. In terms of by and large, this is the way I always have my students look at the velocity graph. They'd measure the slope to find the acceleration. You can actually look, graphical analysis calculates the acceleration. You could show that data instead. And we know that it's during this portion right here and during this portion right here that the 2 are accelerating. If you could choose to do it like that, you would you'd want to do the statistics feature, so you get like an average acceleration during those portions where it's speeding up. I feel like it takes a little bit more work to kind of interpret it, an acceleration graph, and you're likely to get see more noise at the acceleration level than you do in the velocity and the position level. And that's just because that's just a result of the way a numerical derivative works. Any bit of noise or error in the first layer gets amplified in the second. I'm going to go back to my velocity data here. So you might, the way I did it was measuring the slope of the graph using apply curve fit, or you can use statistics to find the average. If you do that, you're going to have a number of runs, and then for each of those runs, the student is going to find an acceleration, and then they want to make like a summary data table. With this much mass, total mass, this was the acceleration. With this much total mass, this was the acceleration. Or you're moving mass from the cart to the hanging mass to measure. Well, with this much net force, this was the acceleration. I have here sample data I collected with just this setup right here. The first graph is net force or acceleration versus net force, and with a nice linear relationship. The greater the net force, the greater the acceleration, just like I expect it to be. Likewise, with the acceleration versus total mass, I end up with an inverse relationship. And they both worked out pretty well. I got excellent data in both cases. So your students, typically they'll be in, half the class is doing acceleration versus mass, and the other half is doing acceleration versus net force. They've collected their data, they've created these summary data tables, these graphs, and now you come back together and say, okay, what does this tell us? And you're going to end up talking, oh, I want to talk, it's too far. You're going to end up putting those 2 together. Well, acceleration is directly proportional to the force and inversely proportional to the total mass. You might, if you're that kind of teacher, you might put them on the board and show how you end up with F equals ma. But yeah.
So
Uh,
Josh,
yeah.
a little while ago, uh, you, well, a little while ago, one of our participants was asking about doing exactly this experiment, but adding friction to the cart, like actually
Ah,
putting the um, the
the
friction
friction
pad on
block.
the
Yeah.
cart. And had we thought about that? And do you think that would be a good experiment?
I think it could be. Definitely, I don't know that I would do that as at the beginning of my unit on dynamics where I was establishing Newton's laws of motion, But once they know, or if I had AP students and this was their second year of physics, or if I want maybe as a practicum, they've had an opportunity, they've used Newton's second law a number of times in the past, and we've talked about net force being different than just a singular force, then it might be a nice practicum where you add on that friction block. Okay, say I'm going to add this static force on here, and I want you to, and you can have them, either predict what the acceleration is going to be, have them say, I'm going to give you 10 minutes, take some measurements here, and I want you to predict what the acceleration is going to be if I put such and such hanging mass on here. Or you could have them use what they do the same sort of experiment, but with the friction pad on there. And you can have them, okay, now that you've seen what this is, how it's different from what we did before, I want you to tell me what the force, the magnitude of the friction pad, the friction force is on the cart that way. That might be a nice extension. They know about balanced and unbalanced forces. They know about adding forces, subtracting forces from each other. They know about Newton's second law, and they know this setup. They've already collected data from it before, and so then they can go back and kind of put it all together to show that they understand those things. All right. I want to talk a little bit about one other different piece here, and that is we have a fan that mounts to the carts. This is what I'm showing you right now is actually a sensor cart. That means it has a fifth wheel here that's encoded that transmits motion data to graphical analysis. But it'll also mount to just the kind of cart that I've been using here with my modified Atwood position. And you can use these as a way of easily creating force on the object. If you want to measure if you want to do Newton's second law with this, you can do that. You'll want to use a force sensor to measure the thrust, the push against like have it run against a force sensor or something like that. This has a force sensor built into it, to measure how much thrust there is at each of the thrust levels of the fan. If you want, you could put multiple fans on a single cart. If you want to do it that way, you could have one fan, two fan, three fans sort of thing. This makes it easy to talk about it conceptually because it's like you can vary mass very easily by adding and removing mass. And you can change the force on it very easily just by changing the thrust level. So that's a different way of doing Newton's second law, same sort of idea. If you're interested in doing it that way, I did a webinar 2 months ago, I think, that was just about the cart fan. And you can go see there, there's a link here in the thing. You can go, there's a section there about measuring Newton's second law using the cart fan. I want to bring that up because it's a nice alternative. What we're doing here with the modified Atwood setup, everything you need to do this, besides the motion detector, comes with a cart and track kit. So you just need a motion detector or a photo gate to measure the motion, and that's it. Besides that, this one you need the sensor cart and you need the cart fan. So it takes a little bit more equipment or that sort of thing. All right. So now students have this idea, that the acceleration depends on the net force on the object, and it depends on the total mass of the object. So what does that tell us about our superbike? Why can it outsprint these other vehicles? Well, this is where we hope that they understand that even though it has a smaller engine, so there's less net force on the motorcycle than there are on the other ones, it has a much, much lower mass and therefore can achieve a greater acceleration than the other ones. I remember when I was teaching, this was, I don't know, 15 years ago or so, there were some, within a couple of years of each other, there were two professional football players that got in trouble for riding motorcycles when they shouldn't have. One of them was a receiver, and he like injured himself. The other one was, I remember Ben Roethlisberger, who was the real, superstar quarterback for the Pittsburgh Steelers. I remember this because I grew up in Philadelphia and was an Eagles fan, and so I had a little bit of Schadenfreude when Ben Roethlisberger crashed his motorcycle and couldn't play. Anyway, so it's really, at the time, I thought it was really interesting because one of the things that was brought up in the news was that in a lot of contracts for these NFL players, it explicitly says that they're not allowed to ride a motorcycle. And I thought that was fascinating. And I think when I was thinking about this lesson, part of me wanted to start with that phenomenon. Why would they do that? Why would they single out motorcycles? And it's because motorcycles have really big engines and relatively big engines and relatively small mass, which makes them really exciting and really dangerous, And anyway, I thought that was a cool piece of context that you might, like I said, I would be tempted to start the lesson that way and talk about why. Well, why would they explicitly call out motorcycles? Then you'd also want to, of course, expand Newton's second law to other areas. You talk about throwing more and more stuff in your grocery cart at the grocery store, and why is it harder and harder to push this thing? Or you might look at, I'm a runner, and so it's always amazing to watch the Olympics, and you see these sprinters that are like ripped. They look so strong, and then you look at the marathon runners, and they're all real lithe and long, and it's like, why are they built so much bigger? Or if your students have come to you from chemistry, and your chemistry teachers have talked about, like, say, mass spectrometers or whatever, that's a great way to kind of rope in these another phenomenon, another device that takes advantage of Newton's second law. We definitely want students to be able to explain the phenomenon, but then we want them to understand the principles that explain that phenomenon show up elsewhere as well. We want them to see those applications. All right. Have I missed anything, Fran?
So the only other thing that came up was a question about there being a bit of friction between the cart and track
Yeah.
without the friction pads, and maybe how do students deal with that, or do we deal with that with students?
Yeah. Often, well, it depends. When it comes to your standard physics students, conceptual physics students, the data that you get from this particular setup here, usually it's there, but it's easy to miss. The magnitude of the force of the hanging mass is so much greater than the magnitude of the force of friction between the carts and the tracks that usually it doesn't show up real well. Sometimes, especially if you are teaching an AP physics class and you need to talk about the experimental setup and confounding factors and stuff like that, you might have them estimate the friction. And you can do that a couple of ways, either as part of, with the experimental set you've got, or just, the way that we usually measure cart friction here at the office is we'll set up the track on an incline and we'll roll the cart up and down and measure its motion along the way. And because the friction force aids gravity on the way up and it opposes gravity on the way down, you can see a kink in the velocity graph, and from the amount that it kinks, you can estimate that rolling friction. So like I said, if it's new students or introductory students, usually you don't need to worry too much about the friction. The friction is low enough compared to the other forces involved that it's not too much of a complicating factor. And if it's a AP class, then you probably do want to investigate that, but you'll likely have to have them do some measuring to figure that out.
We got a couple more questions.
Sure.
One is, how far does the motion detector work? So the closest is about 20 centimeters. What's the farthest?
Okay, yeah. So the closest is about 20 centimeters. How far really depends on everything else. You imagine that cone that it can see everything within the cone. The farther away you get from it, the bigger that cone is. And the more likely it's going to encounter things, there's going to be things that mask the motion that you're trying to track. Effectively, in most classrooms, it's around 2 meters. You get past beyond 2 meters, and there's probably enough stuff in the cone that you really can't see things. When I would do graph matching with my students, I would have we would set up our lab desks so it was kind of like lanes, and the lanes were about 2 meters long, and that worked pretty well. If you were in like a gymnasium where you could clear out lots of stuff, like the theoretical, like what that detector says is something like 6 meters or something like that. Whether you actually get effectively get 6 meters out of that, it's hard to say. But for the most part, 2 meters is about what you get in most classrooms before you run into things complicating things.
Okay, we've got a bunch more questions coming in.
Yeah.
So if I use a force and a motion detector, can I see all the graphs at the same time, position, velocity, etc.?
Yes, you can. So as long as all the force and the position are collected, connected to the same interface or connected to graphical analysis together, you can see all of them together, and you can line them up real nicely and look at those together.
All right. And then what masses do you typically use for the hanging masses?
That's a great question, because when it comes to this particular setup, the modified Atwood setup, the kind of like the limiting factor is the pulley, is actually this pulley. It has a real nice low friction bearing in the middle of it. And if you apply too much weight to it, and it's just the weight's just a little bit off, it can like kick, you can push it, end up pushing it off that bearing. And so usually we say the total weight on that pulley should be no more than about 120 grams. You can usually for an experiment like this, you want 5 or 6 data points. And so I usually do go on the lower end. It's not like you need to measure real fast accelerations. You can see, you saw how the data runs that I collected today were only just not even a second long. And so I would do, like I started at these hanging masses. Just the hanger by itself is 50 grams. And then I would step up by 20. And I got to about, I think, 120 grams or so after 5 data points. And that worked out real well.
Okay, another one. Any tips on using the Go Direct cart built-in force sensor?
Oh, yeah. So this is the sensor cart. It has, I think I mentioned before, it has that 5th wheel here. That 5th wheel is encoded, and it allows you to measure the motion of the cart itself. And then there's a force sensor built into it right on the end. Right now it's got this rubber bumper, mounted in there. And when you connect to the cart, that sensor channels place, that's where you'll turn on the force sensor. And if you want to use it, you want to treat that force sensor just like you would any other force sensor. So that means before you use it, you'll want to like zero it in the orientation in which it's going to be used. It'll measure pushes and pulls. It's actually the same load cell as in our other force sensors, so it has like a 50 Newton range. If you want to measure like collisions with this, generally you want to sample really quickly. We're talking like 200, 500 samples per second. If you want to get nice, clean impulse curves, we suggest you use use a hoop spring on this rather than this like kind of dense rubber bumper. That spreads out the impact enough that you get this nice, beautiful impulse curve. Whereas these guys, tend to get a spike, And while that works, it's more satisfying as a physics teacher to be able to see this nice impulse curve that you can do an integral on, that sort of thing.
Okay, and then related to that, if you select the accelerometer in the X direction in the sensor channel, does that measure the acceleration of the cart? We were getting different values from the slope of the velocity graph.
So there are 2 ways. So these carts have an encoded 5th wheel, right? That gives you a position, and then graphical analysis does the numerical derivative to find velocity and acceleration. And then there's also an accelerometer itself, like a 3-axis accelerometer built into the cart itself. So you could get acceleration from that, and you can get acceleration from the encoded 5th wheel. And sometimes you may see like, wait a minute, they seem to be pretty different. And it's a little hard to compare them because the ways in which they find, they measure that acceleration is different. And by and large, if you're doing like motion on a track, you're going to get better data from the encoded fifth wheel, from the position channel that shows up in graphical analysis. And that's because the accelerometer that's built into this has a total range of plus or minus 16 G. So that's like, what is that, like 154 meters per second per second? So that's the range of this thing, 154 meters per second per second. And the kinds of accelerations you get on a track are relatively small, a few meters per second per second. And so it's just such a small amount of acceleration compared to the total range of this that the accelerometer doesn't do a real good job of measuring the acceleration. If you were to put this, hang this from a spring and then then you would definitely, the accelerations there are large enough that you'd get nice, smooth acceleration data. If you were to put this, actually, like put this in your car, you're driving your car and turn a corner or speed up or slow down, the accelerometer in this would do a great job of that too, because the accelerations you're experiencing are on a G or two, sort of thing. Whereas on a track, you're talking about not even half a G, and so it's just too small to measure real well.
All right. So we're getting really close to the end of this. There was one question that was asked that it's not an experiment that I have tried, and I didn't know, Josh, if you had tried it. But apparently the College Board sometimes has questions like you have a hanging chain and therefore it's a variable acceleration because the farther it goes, you have the more mass hanging off the end.
Yeah. You could definitely, well, you could do something like that. Yeah, you'd have to play around with it a little bit. The trick would be to be able to measure. You want your pulley. You don't want your pulley to have too much mass or friction. These little pulleys are great, but they're definitely designed around string rather than like a chain. And another great thing about pulleys, though, is because most pulleys have spokes, it'd be easy to mount a photo gate and be able to pretty accurately measure the acceleration. The spokes make it really easy to measure. Anyway, so the trick would be to find, if you want to use our pulley, to find a chain that is significantly heavier than just like string, but still small enough that it'll roll smoothly across the pulley. I don't know. I'd have to think about what the right way to do that it would be. I suppose
Yeah,
good.
I was kind of stymied too. I've never
Yeah,
tried it, but
that would be fun to do though. We got to find the right. Maybe the trick would be to find the right kind of chain first, and then see what we can do. I guess you could probably do it if you colored the links or put made it easy to track or to see the links. Take some high-speed video and do it in video analysis. I have to look into. Right. Well, I think, Dylan, you want to wrap us up here?
Yes, I do. So we have two things. First and foremost, we are giving away a Go Direct Motion Detector today. So anyone who stuck with us this long has been entered to win. I went ahead and put everyone's names into a random name generator, and today's winner is Lee Sumner. So congratulations, Lee. I have your email in our system already, so keep an eye out for an email from me, and we'll figure out how to get you your Go Direct motion detector. And then the second thing that I wanted to cover with you all, you probably heard me say this at the beginning of the webinar, but just to make sure you all know that it's coming, the recording of today's webinar will be sent out. It usually takes us about 3 to 5 business days to edit it, get it uploaded onto our YouTube and our website. As soon as it's live, we'll email it on over to you guys. So again, could be early next week, mid next week, and you'll have the resources folder at that time as well. So lots of good stuff coming.
All right. Thanks, everyone.